Questions on the homework, I guess? We have 3 today. 1.4, 1.5, and 2.3. I guess we can start on 1.4 and then work our way down.
Number 45.
What does that say?
A, B, and A plus B are all non-singular n by n matrices.
A, B, A plus B are non-singular?
Right.
Okay.
Which means they're invertible, right?
Yes.
So A, open parentheses, A inverse plus B inverse,
A inverse plus B inverse.
close parentheses, B, open parentheses, A plus B, close parentheses, inverse. Show that that equals I.
Okay, so we want to show this. All right. So usually when you want to prove something like this, I'd probably start with a more complicated side. So let's start with here. A times A inverse plus B inverse times B, A plus B equals. Let's start simplifying this.
It would be inverse.
Huh?
It would be inverse.
Yeah. So let's start simplifying this. What are you doing?
The part, distribute the A.
Yeah, we can distribute the A here. The rule says matrix products distribute. Of course, you have to respect the order, right? So if the A is on the left multiplying in, you have to keep the A on the left once it's inside. So this is actually A inverse plus A B inverse times B times A plus B inverse. All right, and A inverse is just the identity by definition. Now what? Distribute the B. So I'm going to do it again. By the way, I'm using the associativity laws here when I can just choose which two I want to multiply first. So I can multiply these two first. So again, that's going to be B, because IN times B is B, plus AB inverse B times A plus B inverse. So this is B plus B inverse times B gives me the identity, so that's just A times A plus B inverse. And of course, B plus A is equal to A plus B. So you have A plus B times its inverse, you get the identity.
Okay.
So just reapply the associativity laws until you break it down.
Yeah.
Could you have multiplied matrix A times matrix B directly? Did that?
No. Because what you would assume in doing that is you can swap these two and then multiply the A and the B. But remember, matrix multiplication is not commutative. So you wouldn't swap. That would be not good in general.
I have a question.
Yes.
So if we have a matrix and its inverse into the operation, but they are not consecutive, let's say the first operation, the A and A inverse.
This one?
Yeah, if we had B in the between, we couldn't like
B in between where?
A and A inverse, for instance. Right.
So if I had A inverse plus B inverse?
No, a product. A inverse times B times A inverse.
A inverse times B
Yes.
times A inverse
A times A.
times A? Okay. Yeah.
So we cannot like simplify that because we have A inverse and A.
No.
No, we cannot.
Right, because you can't swap these two to get this beside each other.
Okay.
There's a topic we're going to do later on where we're going to see things similar to this about diagonalization, but in general, no, that's not going to work. Because multiplication is not commutative. So. Other questions?
43. Show that if A is invertible, AB is equal to AC, then B is equal to C.
A is invertible. If AB equals AC, then B equals C. Okay. Well, here I just assume AB equals AC, then this means I can multiply on the left by A inverse, because I know its inverse exists. It's invertible. So this gives me identity, that gives me the identity, so I end up with B equals C.
And further, this question 45, the part 2 asks, what does it tell you about A inverse plus B inverse? That was part B for number 45. It's like now that you found that result in part A, what does that tell you about A inverse plus B inverse?
What does it tell you about A inverse plus B inverse? Well, it tells you that. So part B, it would tell you that A inverse plus B inverse is not the same as A plus B inverse. That's what it would tell you.
Okay.
Inverses don't distribute across sums. Right? Because if this was the inverse of that, then we wouldn't need the A and the B to get the identity. Right? If these two weren't here, and I just had this times that, I would get the identity. But I had to throw these two guys in there to get the identity. So it means that this is not the inverse of that. So it's just a way of telling you that inverses, you can't distribute powers across sums. Just as you can't do it in algebra, you can't do it here, right?
In that question I thought it is like an operator, like plus operator.
Okay.
It adds A to B because the multiplication of the left side, other than A plus B inverse, it gives you identity. So the left side, we can think that like A plus B, the total of that expression. You understand?
We can think of this as A plus B.
The left side, other than the A plus B inverse, the other part
Okay.
is A plus B. So it works like a plus operator on matrices. Can you say that?
You're saying that
That is like, it
this
works
part
like,
here?
yeah, that only A inverse plus B inverse
Yeah.
works like plus operators on matrices.
Yeah, but not on A plus B. These are just the plus operator on. I don't think that's true.
I mean, in this case, you can think that way, maybe. It's like a plus operator. Instead of that, if you put plus operator, it's gonna be the same.
Oh, if you include all of this.
Yeah.
Yeah.
Yeah, and can we say that?
Sure, but I can't think of a situation where that would be like a convenient thing to know. But yeah.
Yeah, I mean, it's not going to know, but
Yeah.
in this question, you may think that's.
Yeah, it's also true. But I'm pretty sure this is what they wanted you to conclude.
And can we further say that A inverse plus B inverse is equal to B plus A or A plus B? Or
Is equals to B plus A? No, that's not true.
oh, so you can't say equal to the inverse of A plus B inverse.
It's just saying the inverse of a sum is not the sum of the inverses.
Okay.
Is basically what you're supposed to get from that. So maybe one more question from 1.4. Huh?
53?
What?
53?
53?
Which was a proof of one of those identities, which is
Okay.
A times, in parentheses, B minus C is equal to AB minus AC.
Okay, so we want to prove this?
Yeah, but then you couldn't use the same, like, IJ You have to make that different.
You couldn't use ij. Well, there are tons of ways to prove this. There's one way where you can literally just write everyone out, like write this as A11, A12, blah, 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 write out the whole thing, and then do the same for B and C, and then actually do the arithmetic. That would kind of take forever though. I'd probably use a shorthand for that. But yeah, you could do it that long way, just brute force it. But then if you look at what multiplication looks like on an element by element basis, which is basically the dot product, you'll be able to figure it out. So for example, notice what this is not starting the proof, but I just want you to notice a pattern here. So that when I tell you the proof, it won't confuse you. Okay, so pretend that this is A and this is B. Right? And I'm looking at the first row here, A11, A12, all the way up to A1n. And let this be, say, the first column, B11, B21, B31, all the way down to B and N. I need the number of columns here to be the number of rows there, so this is Bn1. Okay. So let's say I'm just looking at the first row times the first column, right? I'm just going to illustrate something here, right? What would that actually give us in the result?
A11, B11.
Right, the entry here, right? What would that entry actually look like? Well,
Summation.
A11 times B11 plus A12 times B21 plus dot 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 A1n times Bn1, right? That's what this guy would look like, right? The first element in the first row, right? Now notice what this guy is. I can write this, for example, as a summation of a bunch of elements. Let's say use K. Right? Notice the pattern that I'm seeing. The outside numbers are always the same, right? And the inside numbers are also always the same. Right? So this is actually a sum of something like A-I-K times B-K-I. Right? So in the product, the ij element in a product I can write as this. It's just a dot product that works in this way. So now, let's work on this. So let's do this notation. What is the ij element of this matrix, right? Well, that's just going to be the sum of k goes from 0 up to n. I'm assuming n is the number of rows in A. Of the A I K times B minus C K I, right? I'm just applying this formula to these expressions, right? I'm just looking at this as the second matrix, that as the first matrix, right? So I can write it as that. But now in these summations, these guys are real or complex numbers, right? So this is actually just k goes from 0 to n of A I K times B K I minus C K I and A I K B K I minus A I K C K I. Remember from Calc 3, summations actually distribute across sums. so easy to write infinity there. So this is aik bki minus the summation.
They have to be J, I guess. C, K, J, A.
Yes. Because if I was to take the first row times the second column, then all these guys would be 2's. So yeah, the columns can be different. But the inner numbers would have to be the same. So, here. So this would be A, I, K, B, K, J, C, K, J. So now this guy here, I recognize this as the ij element of A times B. Minus, this is just the ij element of A times C. And that's it. If you wrote this out, brute forced it, it would be pretty much exactly the same proof, except you'd be writing out a long string of numbers, and it would be really annoying to actually get it done. But you can use something like that. Questions on 1.5? So a lot of times when they ask you proofs like some elementary proofs like this, a good strategy is to either brute force it, just write down an arbitrary set of elements for the matrices, and then multiply them out. If you can figure out a way to use the ij element only, then do it. It'll actually save you a lot of writing and a lot of work. Yes, but we really should be moving on. Let's go to 1.5. Questions on 1.5? Okay, what does that say?
Prove that if B is obtained from A by performing a sequence of elementary row operations, then there is a second sequence of row operations which, when applied to B, recovers A.
So that just kind of screams elementary matrices to me, right? So whenever you're asked about row operations, a good technique is to use elementary matrices to represent them. So let E1 to Ek be the set of elementary matrices that obtains B from A. This means that if I multiply these guys times B, I get A. But this actually means, I know each elementary matrix has an inverse, right? So I can actually just multiply by the inverse on both sides. Ek to E1 inverse of Ek to E1 B equals Ek to E1 inverse times A. So this gives us B. And over here, this guy is actually E1 inverse, E2 inverse, Ek inverse times A. So this is just a sequence of row operations. get B back from A. Just take the inverse row operations in the opposite order, and that would be a sequence of row operations to go backwards. Other questions? Going once, going twice. Okay, 2.3. What? 33. Okay, what does that say?
If A is equal to the matrix, D/3 matrix, it is ABC going across. Yeah, ABC, D, all the way to I.
Like that? 3 by 3? Okay.
Assuming the determinant of A is equal to -7, find 3A, the inverse of A, 2 times the inverse of A,
Wait, oh, so these are, you want the determinant of what?
3A,
3A?
the determinant of A inverse, determinant of 2A inverse, and the determinant of 2A in parentheses, and then inverse that. And then the determinant of the
Determinant of A transpose?
no, not really. It's switched.
It's the transpose, but the columns are switched.
Yeah. So the first row is ABC. I'm sorry, first column is ABC.
Oh, okay, so he's the determinant of,
ABC is the column. And then the second column is GHI. Third column is GEF.
D, E, F. Okay,
And it says also determinant of A equal -7.
oh, we have that, I wrote that here. Okay, let's go. What's the determinant of 3A?
3 cubed times -7.
Right, that's gonna be 3 cubed times -7, which is something big, right? So that comes from the rule that determinant of K times A is just K to the N times the determinant of A, where N equals number of rows. So that's gonna be A, B. Determinant of A inverse. Right, it's 1 over the determinant of A, that was another theorem, so that's just -1/7. Determinant of 2A inverse. Two to the power 3 times the determinant of A inverse. That's going to be 2 to the 3 times -1/7, which is what, -8/7. D.
-1/56.
How'd you get that?
1 over K to the N determinant of A.
Well, first you have to apply that rule that this is just the determinant of 1 over 2 times A inverse. Right, because there's a theorem that says since if you take KA and invert that, it's 1 over K A inverse. So I can just replace that 2 with a half. and then you would just have a half to the third times minus 1 over 7 plus minus 1 over 8 times 7 e How can you figure out the determinant of this guy?
This is the transpose, but we change one row. The second one.
Notice that this is equal to
Minus the determinant of A. Because we
determinant of. Basically, they took the transpose and then they
exchange the columns.
A transpose with 2 columns exchange. So that's pretty much, once you exchange 2 rows or 2 columns, that means you negate the determinant. So that's just a negation of the determinant of A transpose. But the determinant of A transpose is what?
It's the same.
It's the same as the determinant of A. So this would be positive 7. Anything else from 2.3? So, okay, pass the homework up to the front. And we will move on. Okay, just sent everyone the answers to these 3. So you have that in your email. We are going to jump to chapter 4. Chapter 3 is basically chapter 10 from top 3, so it's pretty much exactly the same content. So we're jumping to chapter 4, where we're going to talk about vector spaces. Woo! Of course, to start out, I'm going to have to tell you a lot of definitions, because we're going to be doing a lot of different things. There's going to be a very different feel to this section than the last section. But yeah, vector spaces are very important. So we went through matrices, to figure out how to operate them on them, do addition, do scalar multiplication, found out some properties, how some matrices are invertible. How do you know a matrix is invertible?
The determinant is not 0.
The determinant is not 0, right? And if such a matrix is the coefficient of any system, what do we know? X equals B. Tell me about that system if A is invertible. Huh?
There's a unique solution.
Has a unique solution. What about this system here? Only the trivial solution. What is the reducer echelon form of A? Okay. All right. So you know all that stuff. When we were doing all these computations, you might have thought it was neat, maybe not. But the point of all that was to help us do the rest of the thing, right? Matrices are just a tool that we're going to be using to really talk about what we care about. So remember in day 1, I told you what linear algebra was about. It's the study of vector spaces and linear transformations between vector spaces. Matrices happen to be able to represent linear transformations between multi-dimensional vector spaces. So that's why they're useful. They're going to really help us out to talk about what we really need to talk about. And vector space is going to be one of the first things we're going to be describing. So let's actually jump into it because we spent a lot of time. This is going to be a long one. Oh, by the way, just a note here. I will do that later. Because in 4.1, your textbook calls it real vector spaces. We're going to be thinking more generally, right? We're going to be doing F vector spaces. Right, the name in the front just comes from who your scalar field is. So real vector spaces just means vector spaces where the scalars are all real numbers. But we're going to be thinking a little bit more generally. So let's actually just jump into that definition. Let's talk about this. This is really bad. Let V be a non-empty set of objects. With binary operations. Addition and scalar multiplication defined. Everything's going to get a lot more general, right? So I put these words in quotes because I don't want you to think addition when you think addition, right? I just want to mean by addition, we mean a rule to combine two elements V, two elements, let's give them names, U and V of V, to get another element of V. Which we denote by U plus V. Scalar multiplication. The product of a scalar called K over C with an element U in V to obtain KU, which is also about so let U be W the elements V and how many scalars are in K and N the elements of F. Then V is called a vector space following axioms hold. There's a list of 10 things that we're going to look for to determine if something is a vector space. 1, if U and V are in V, then so is U plus V, right? So whenever I combine two elements with my addition, I get another element that's in V, right? This is called closure under addition. So that's the first thing. If I combine two elements with my rule for adding stuff, and I will always get another element in that original set. It's called closure under addition. I have, addition is commutative. U plus V must be equal to V plus U. This is commutativity. Mutativity of addition. 3. I have associativity of addition. So U plus V plus W is equal to U plus V plus W. There exists an object which we will call 0 in V, such that 0 plus U is equal to U for every U in V. If U, we know this notation, right? An element of the set. Okay. So if U is an element of V, if U is someone in V, then there exists a guy which we will call minus U in V, such that U plus minus U equals 0. If K is an element in my field, which we're using F as the real or complex numbers, and U is an element of V, then K times U is an element of V. This is called closure under scalar multiplication. Scalars distribute across sums. So K times U plus V is equal to KU plus KV. K plus M, I think was the other guys. K plus M times U is equal to KU plus MU. 9 Km times U is equal to K times MU. 10. 1, which I'll like to use a bold one, times U is equal to U, where 1 is the multiplicative identity. Okay. Whew. Those 10 things make up what we call a vector field. Now you might be looking at this and wondering, isn't that all kind of obvious? So here's the thing. One of the reasons why math is a very powerful tool is because we can generalize it and apply it to situations in real life and try to figure things out, right? It's an abstraction. So basically, even the things where we make an abstraction, usually what math people do, they want to make abstractions of the abstraction, right? So, you know, math started out with simple arithmetic where you're just counting out how many apples and oranges you have, or, you know, the area of your field. But then you want to apply this more generally, so you develop algebra, right? And you try to generalize this notion of adding two numbers, right? And then when you translate high enough and we start talking about vectors in R3 and all that stuff, now you want to generalize that idea, right? And we want to make things very much more general. So far when you've been seeing plus, you just think of it in the usual way. I just have these two numbers, you know, based on the laws of arithmetic. But here we're thinking of things very general. Our vector space consists of, I call objects, meaning they could look like anything, as long as it obeys these 10 rules. Also, plus and minus and even multiplication doesn't have to mean what you think it means. It can be defined anyway. It's just a rule. And I can make up my own rule, right? So, probably back in the early days when you were doing math and, you had those people who didn't like math that try to like get contradictions. Like, why is 1 + 1 = 2, you know? Because, you know, if I have a bunny and you give me one bunny, I could end up with 3 bunnies, you know? And they make up all these things. And so, yeah, okay, what about generalizing to that situation? How about I do that as a rule of adding? Take this guy, add it to another guy. The rule is I get that plus 1, right? I can just define my addition to be that, to cover that situation that this person talks about, and I can do math on that situation. I can define addition to be anything I want, as long as I can combine 2 elements and end up with a 3rd element that's still in the set, right? But it can be any rule that I want, right? Even multiplication, I can define it any way I want. We're really thinking really general here. And I write this in the notation that you might have seen from Calc 3, but it doesn't have to be vectors from Calc 3. It could literally be anything, and we're going to be doing that. These guys could be polynomials, they could be functions, they could be matrices, they could be anything, right? As long as they fulfill this criteria, when I tell you what my 2 rules of addition and scalar multiplication are, it forms a vector space, right? We're thinking very general here, right? So don't think any of this is obvious because it seems obvious. The idea is we're trying to abstract something that is intuitive to us already, right? You'll notice that vectors from Calc 3 would obey all these rules, right? So we know we're familiar with that kind of space, so now we want to generalize and talk about other kinds of sets that behave in the same way, right? So we can talk about unfamiliar objects in terms of things that we actually know a lot about, right? So that's where we're going to go. We're going to be generalizing like everything. So in section like 4.1 and 4.2, we're going to be breaking ourselves out of old habits of taking everything for granted. And where can I start erasing? And I'll be giving you some examples to see what I'm talking about. Also, even things like this, some people might like, whoop. 0 plus this, of course there's a 0, and of course there's a 1. These guys don't have to be what you think they are, right? So we're gonna do all that, examples of everything here. Don't want to tell you that. I can just tell you that, it's not terribly. Just a list of things you might want to do when you're approaching the question of, am I looking at a vector space or not? Right, 1, identify who are the vectors. What the operations are. check closure under addition and scalar multiplication. And 3. Then confirm the rest of it. Confirm the remaining axioms. So a lot of times these are the first guys to mess up. So you normally want to check those first. Another thing would be to check is if there is 0 element in the thing. That also messes up a lot of the times. So so how about some examples and non-examples? Example. R2 is a vector space. Where I can write elements like this, and U1, U2 are elements of the real numbers. I can define addition this way. If U is equal to U1, U2, V is equal to V1, V2, then U plus V is just the sum of the corresponding entries. And K times U is just the product of the corresponding entries with K. With these operations, R2 forms a vector space. You can define your addition and scalar multiplication this way, and you can go through this guy and figure out that all of these hold, right? So obviously here we have commutative addition because we get normal addition inside the components. Associativity, we'd have that inside the components. There exists a 0 vector, namely the vector where I have 0 here and 0 here. There exists a negative for any vector, so the negative of u would just be minus u1 and minus u2 in the components there. What else? Yeah, if u1, u2 is a vector, then ku1 and ku2 is also a vector in R2. We have this, you can check these guys. 1 would just be actually the number 1 from the real numbers. Yeah, so that's actually a vector space. R3 is also a vector space with a very similar operation. We can go even more generally. The n-dimensional real vector space, Rn, is a vector space. So Rn is basically the set of all elements that looks like x1, x2, all the way to xn, where xi are real numbers. With, I can define addition to be just, again, the sum of the components, x1 plus y1, comma x2 plus y2, comma xn plus yn. And k times a vector here, x1, x2, all the way to xn, is equal to just kx1 all the way to kxn. If I define addition and scalar multiplication that way, in the usual way, I get that guy. And I can go through all the 10 axioms and realize that, yeah, they would still work. We can get even crazier and say something like R infinity is a vector space. R infinity is the set of infinite dimensional vectors, x1, x2, going on forever, where xi are in R. With, again, x1, x2, with plus y1, y2, just adding corresponding entries. And scalar multiplication. Is equal to just multiply each component by that scalar. These operations are called the standard operations. On Rn or R infinity. Defined in the usual way that we usually think about them, but we don't have to do that. Let's actually so there are a bunch of examples. There's another one. Define W to be a subset of R2. Such that if U and B are in W, K is in R, then if I take U plus B, which is U1, U2 plus B1, B2, is that a vector space? Huh? Why is it not a vector space?
Because we don't know if U plus V, U1 plus V1 is in W. It's not true for all W's.
No, yes it is. Because addition is defined.
Well, we're over, R is the field, right? So definitely U plus 1, U1 plus V1 is in R, and U2 minus V2 is in R.
Yeah, but it's not in W. Yeah.
There's nothing to say here that it won't be in W. Is it a vector space or not?
Maybe. Depending on what W is.
Think of it as R2. Think of it as R2, right? W is equal to R2. Take two vectors in W, which is two vectors in R2, and I do this. I define my addition this way. In the second component, I put a minus instead of a plus. Vector space or no?
Yes.
It's not a vector space.
Yes. Why not?
Why not? Exactly.
The U2 minus V2, isn't that it? That's the problem.
This is the problem. Why is that a problem though?
Because it's the vector space, it's supposed to
commute.
Yeah.
Right? Notice that u plus v is not always the same as v plus u. They can be different in the second coordinate. Right? So if my u2 was a 1 and this was a 2, then u plus v is actually 1 minus 2, whereas v plus u would be 2 minus 1. They disagree in the second coordinate. So I don't have commutative addition here. So if I define addition in that weird way, it's not a vector space anymore. What about if I define u plus v to be equal to u1 plus v1 comma 0? Ku is the normal operation. Ku1, Ku2. Is that a vector space? If I define my addition that way.
Yes.
How do you know it's a vector space?
Because v plus u is v1 plus u1, which is commutative,
I think.
and the other is 0.
You just basically told me the definition. That's not what we had to check. What do you say?
Isn't it no? Because
Why would you know?
in the second, with the addition in the second part, that's if it's 0, then doesn't that mean that it's not commutative? Because if it's
No, this would be commutative. If I put v plus u, I would just get v1 plus u1. So it swaps. It's commutative.
0.
It's not a vector space. Why?
Because if it's 0,
Who is 0?
it's
Right? Tell me what element that I can take and I add to u and get back to u itself. Right? Let's say my u was the vector 1, comma 1. What could I possibly add to that to get back 1, comma 1?
it's a 0 vector.
Nothing. There's no such thing.
It's a 0 vector, right?
Well, as in 0, comma 0?
Yeah.
Well, if I add that to 1, comma 1, according to that rule, the result would be 1, comma 0. So the 0 vector doesn't work. Maybe another vector works. This is what I'm trying. 0 does not mean normal 0. We have to think generally here. Let's actually figure it out. Let 0 be another two-dimensional vector. Call it AB. Right? I want AB plus this to give me back that. Right? So then 0. Now if I take AB plus 1, 1, I want to get back 1, 1. Right? But according to this rule that I just defined for addition, what would this plus this be?
1 plus A. I mean,
A plus 1,
plus 1,
comma,
0.
comma 0. Right? Now that's a contradiction. That's never going to be true. So 0 does not exist here. Not a vector space. The set of n by m matrices. Vector space or not a vector space?
Vector space.
is a vector space. With addition and scalar multiplication defined in the usual way. Right? Go through matrices and that list of 10 things for an n by m matrix, all 10 would be fulfilled. My 0 in this case would be the n by m matrix with all zeros in the components. Example, let W be a subset of the 2 by 2 matrices with A, B, C, D plus E, F, G, H equals A plus E plus 1, C plus G plus 1, E plus F plus 1, E plus H plus 1, and a scalar times A, B, C, D is just what you think. K A, K B, K C, K E. Is this a vector space with that definition of addition? Right? We add one bunny and another bunny and get an extra bunny. Is that operation a vector space?
Sure.
With these sets? Are you guys just randomly guessing? There's a 50% chance I'm right. He'll never give us 3 no's in a row.
I wasn't randomly guessing,
Okay, how do you know it's a vector space?
because addition commutes,
Yeah, because you just switch these two, that'll be fine.
and there's totally a 0.
What's the 0?
I don't know. That was a guess.
What would be the 0 for this set with this operation?
-1. -1.
-1, -1, -1, -1 would be our 0 here,
Yeah.
right? If
That's
I
right.
add that to this, I would get itself back. Because that -1 is going to kill this extra +1 that I added here.
That's what I was
Right?
getting at.
So my 0 is not just 0, 0, 0, 0. It can literally be anything, right? Think more generally. Right? You just have to check that when I add something to this, I get back itself. That's how we define 0. Right? And obviously the scalar 1, real number, is the scalar to get the unity. And yeah, it's actually a vector space. You can go through and check everything. How about this? The set of invertible matrices. Is a vector space or not a vector space? Is a vector space? Yeah, I'm only looking at the invertible ones though. I'm looking at all the invertible matrices. Right? I know the set of all n by m matrices is a vector space, but what if I only take the invertible ones? Right? I take the set of all square matrices that are invertible. Hmm?
It's not.
It's not
Because
justification.
when you add them,
Yeah.
doesn't.
Yeah, closure under addition fails. You can add 2 invertible matrices and the result doesn't have to be an invertible one, right? Right, so for example, if I have 1, 2, 3, 4, right, then I know that's invertible because the determinant of A would be 4 minus 6, right? Minus 2. And if I have another matrix, let's just say the negative of that, then the determinant of B is also negative 2. But then what is A plus B? That would give me 0, 0, 0. The determinant is 0. So it's not invertible. Right? So I can add two invertible matrices and get something that's not invertible. So this is not a vector space. So if I look at all invertible matrices, I don't have a vector space. Are there any more examples? Sure. There are tons of examples. I want you to get used to some of them. We will be using them later on, so I guess I'll spend some time defining a bunch of them. We're still doing examples. Set of all functions on minus infinity to infinity over f. By the way, when I say a set of something over f, I mean f is the scalar field. With, if I take f of x, f plus g as vectors is just f of x plus g of x in the function world, and k times f is just a constant times f of x. This is a vector field. Vector space. You can go through and check that with functions, all 10 things in the list work out. You look at only the polynomial function, with addition and scalar multiplication defined the way you usually do. That is a vector space. Set Pn, which is a guy we're going to be talking about all the time, which is just the set of polynomials with degree less than or equal to n is a vector space. With the usual addition and multiplication. What are the vectors? What are the examples that I want to tell you about? Well, I guess I could do that. There's the trivial vector space. Literally a set with only 0 in it. So this is where B is just a set of the 0 element. With usual addition and scalar multiplication, that's a vector space. Fulfills all 10 conditions. We got that already. We got that already. Got that already. Equals the complex numbers with u plus v, find the usual way. And ku, if I take that to be u divided by k minus 2 squared plus 1, that's how I would define my scalar multiplication, is a vector space. go through, you check all the 10 things in the list. You get it. Notice that your 0 is the number 0. What is your 1 in this set? One is the number 2. Right? If I multiply this by a 2, I would actually get u itself. Right? So 2 times u gives me u, therefore the number 2 is my number 1. Other examples? Oh, well, I think we're done with examples. But your homework will have a lot more examples, right? So basically it's get out of your old habits of thinking, oh, 0 is just 0. No, this is just take the negative. It's not going to work anymore. We're going to be working far more generally. Things will not be as they always appear to be. At the end of the day, you have to go back, you have to check your list to make sure that you're satisfying all the conditions. Next time we'll prove some theorems about vector spaces and continue with subspaces and hopefully things like span and linear combination. So no homework due Monday, we'll just continue. Yes.